Sets of sets. Recall that elements of a set can be anything whatsoever. So for example, the set A might consist of cat, France, and 5. The set A consists of an animal, a country, and a number. So indeed, elements of a set can be anything whatsoever. In fact, elements of a set can even be other sets. So for example, if the set A consists of the single element cat, we could come up with another set B which consists of two elements, namely cat and the set A. You can also write down B as the set which contains cat and the set which contains cat. True or false? Is the set A equal to the set B? No. The set A consists of one distinct element, namely cat, while the set B consists of two distinct elements, namely cat and the set A. So the two are definitely not the same as each other. Here's another true-false question. Suppose that as before, the set B consists of cat and the set containing cat. Now let's introduce another set C. Now the question is this: are the two sets the same as each other? Yes, they are. The reason is that going by our rule that duplicate elements do not count, we can eliminate certain elements from C. So this cat is a duplicate of this cat, so we can eliminate the first cat, leaving just the yellow circled cat. Similarly, this cat is just a duplicate of this cat, so we can eliminate the first circled cat, again leaving behind just the yellow circled cat. And so we now see that the set C is really just the same thing as the set B. Here's another. Is the number 5 the same as the set which contains the number 5? No, it's not. The important point here is that an object is different from the set which contains the same object. Now suppose we have the set A which consists of dog and the set B which consists of the set containing dog. True/false question. Is the set A an element of the set B? Yup, it is, because the set B is really just the set which contains the set A. So A is indeed an element of B. Here's another true/false question. Is the set A the same as the set B? No, it's not. Just like the set which contained the number 5 is not equal to the number 5 itself, similarly, the set B, which contains just the set A itself, is not the same thing as the set A. Finally, is the set A a subset of the set B? No, it's not. Remember that in order for A to be a subset of B, it must be the case that every element in A is also an element of B. However, in this case, the only element of A, which is dog, is not an element of B. Therefore, A is not a subset of B. Let's make sure you really get this. Suppose that as before, A contains dog and C is a set consisting of two elements. The first is the set containing dog and the second is the element dog itself. Now, the questions are, is A an element of C? Is A equal to C? Or is A a subset of C? A is indeed an element of C because C contains as one of its elements the set A. Similarly, A is indeed a subset of the set C because every element in A, and in this case there is just one element in A, namely dog, is also an element in C. Therefore, A is indeed an element of C. However, A is not going to be equal to C. The reason is that A consists of just one element, namely dog, while C contains two distinct elements, namely the set A itself and the element dog. So the two sets are not the same as each other. True or false? A set can never contain itself. That is to say, if we are given a set S, it cannot contain itself as an element. True. We can now give a little history of set theory. It turns out that historically, a failure to insist that a set should never be able to contain itself led to a disastrous paradox known as Russell's paradox. To better understand Russell's paradox, let us first consider an analogous paradox known as the barber paradox. Suppose that in a small town, Barbara the barber cuts the hair of everyone who doesn't cut his or her own hair. We're going to insist that Barbara follows this rule very strictly. She cuts exactly the hair of those people who don't cut their own hair, and she doesn't cut the hair of those who do cut their own hair. So now the question is this: does Barbara cut her own hair? Well, there are only two possibilities. Either she does or she doesn't. If she cuts her own hair, then going by her rule that she cuts exactly the hair of those people who don't cut their own hair, this would imply that she doesn't cut her own hair. This is a contradiction. On the other hand, if she doesn't cut her own hair, then going by her rule that she cuts exactly the hair of those who don't cut their own hair, she does indeed cut her own hair. Again, a contradiction. So in either logical possibility, we arrive at a contradiction and hence we have a paradox. The Barber paradox is very much analogous to Russell's paradox, discovered by this guy over here in 1901. Suppose that S is the set which contains every set that does not contain itself. We are going to insist that S follows strictly to this rule. It contains exactly those sets that do not contain themselves. It does not contain any other set. Now the question is, does S contain itself? There are two logical possibilities. Either it does or it doesn't. If S does indeed contain itself, then going by our rule, this implies that S does not contain itself. This is a contradiction. On the other hand, if it doesn't contain itself, then going by our rule that it contains every set that does not contain itself, this implies that it does contain itself. Again, a contradiction. Hence, in either logical possibility, we have arrived at a contradiction, and hence, this is a paradox. It was Russell's paradox which led to the realization that if we wanted to develop a satisfactory account of set theory, then we would have to insist that a set should never be allowed to contain itself. In modern set theory, this principle or property is enforced by the imposition of the so-called axiom of regularity. I've already digressed quite a bit, so if you want to learn more about this, you can look it up on your own. I shall end this video with a few words of wisdom.
One last question. Suppose, Lord Russell, this film were to be looked at by our descendants, like a Dead Sea Scroll in 1,000 years' time. What would you think it's worth telling that generation about the life you've lived and the lessons you've learned from it?
The moral thing I should wish to say to them is very simple. I should say, love is wise, hatred is foolish. In this world, which is getting more and more closely interconnected, we have to learn to tolerate each other. We have to learn to put up with the fact that some people say things that we don't like. We can only live together in that way. And if we are to live together and not die together, we must learn a kind of charity and a kind of tolerance, which is absolutely vital to the continuation of human life on this planet.
In the next video, we'll learn about set builder notation. You can go to this next video by clicking on the link at the left of your screen. Or if you'd like to go to the start of this series of videos, you can click on the link on the bottom right of the screen.